And prior to CMU, Dr. Liu was a postdoc at Stanford Intelligent Systems Lab, and she received her PhD from UC Berkeley and her bachelor's degrees from Tsinghua University. Her research interests lie in the design and verification of intelligent systems with applications to manufacturing and transportation. She is an author of the book, Designing Robot Behavior in Human-Robot Interactions, with the CRC Press in 2019. She initiated and has been organizing the international verification of neural network computation since 2020. Her work is recognized by NSF Career Award, Amazon Research Award, and Ford URP Award. Changliu, take it away.
Thank you. Thanks for the great introduction. I just want to make sure everybody can hear me and the slides is showing well. Yes. Okay, great. Yeah. So today I'm going to share with you some of our current work on how to safely learn, predict, and coordinate for autonomous driving vehicles. So these are two videos. The left video, probably a lot of people have already seen. It's a crazy intersection. Although this is this is kind of somebody is performing to get this video, but I also took another like normal intersection in China. As we can see, even in those normal intersections, it's very busy and there's tons of interactions among vehicles with each other, and they need to negotiate the right-of way, and they even need to pass each other like very narrowly. So this is still challenging for autonomous vehicles to do. What our research is aiming to like improve the capability of autonomous vehicles so that they can like achieve almost similar performance. And in particular, in today's talk, we are going to discuss how can we drive in these complex scenarios. And we are going to answer 3 questions. Maybe not fully answering the 3 questions, but just discuss these 3 questions. First is how to safely learn the driving policy for the Ego car. And then is how can we safely and accurately predict the behaviors of other vehicles. And then finally, given like multiple vehicles at a busy intersection, how can we coordinate those vehicles? So let's look at the first topic, how can we safely learn the driving policy? It's great that my talk is after the previous talk, which already introduced the CDF. So conventional approach is to add a kind of safeguard after the nominal control policy of the vehicle so that they can kind of filter out the unsafe behaviors and also generate some like emergency safe behaviors, such as if the front vehicle decelerates, then the vehicle can generate like a detour, emergent detour when it is detected. And this works very well in a lot of problems, but in some cases, this safeguard may conflict with our policy and result in some deadlocks. And the question we want to explore is how can we do an integrated learning? That is, we'll try to internalize the safeguard directly towards the policy itself and get an integrated safe policy. And in the following discussion, I'm going to share with you how we can do that. But before that, let's get one step back. It's actually not so trivial to design the safeguard using the control barrier function approach or other approach as is discussed in the previous talk. That is mainly because we have a lot of uncertainties in the system, and also there are some dynamic limits. And here, let's just consider the dynamic limits. Under the dynamic limits, for example, the acceleration constraint, it's very challenging to ensure that the safeguard is persistently feasible, which means given any state, there exists feasible safe control within the control limit. Now let's look at why that is our problem through this graphic view. So a control barrier function approach or any other type of like maybe safety index approach all belong to this energy function-based safe control idea, where we design an energy function denoted as phi, such that the safe states are with low energy and other unsafe states are with high energy. And if we can design our control law to be energy dissipating, then the system will gradually converge to the safe states. And that idea is illustrated here. So we have this energy function. The red one is unsafe, while green one corresponds to safe states, where the horizontal plane is actually a state space, and the blue area is a zero sublevel set of this energy function, and it corresponds to the safe region in the state space. And for any points on the state space, with the help of this energy function, we can derive a constraint on how this state should evolve in the next few time steps. For example, if we're already in an unsafe area, we should evolve like going towards the safe region, that is by decreasing the energy function. If we're on a boundary, then we should not go up, and then we can stay like at the same zero sublevel set. And if we're already safe, then we can go any direction. And these constraints are actually on x dot. And if we consider the vehicle dynamics, then we can translate the constraint on x dots, the evolution of the system, to the constraint on the control space using this type of dynamic equation. And then this corresponds to a constraint on in the blue area in the control space. And considering the system control limits, for example, acceleration limits and the maximum turning rate, there's a bound on how big the control we can apply. And in order for this type of safe control to work, we need to make sure there's non-empty intersection between the control limits and the computed safe actions. Yeah, so it's non-trivial to design this energy function to ensure there's non-trivial or non-empty set of safe control at any state. So usually for the safeguard approach that's added to nominal policy, we need to spend a lot of effort designing the proper energy function or the barrier function. And so then combining with the earlier question, that is, can we internalize the safety safeguard? Then the question we want to ask, and also the method we want to explore, is can we simultaneously learn how to design a safeguard as well as to learn an integrated safe policy? Yeah, and the next we're going to introduce that method. So actually, if we want to synthesize a proper safeguard, here we start to call it a safety certificate, because it's not going to be an actual guard to our policy, but a kind of constraint during the training of our policy. So if we want to learn that, what we need to ensure is, as we said, the persistent feasibility. That is, at any time step, there's non-trivial safe actions or feasible actions that can dissipate the system energy. And then with this requirements, then we can write the synthesis problem as an optimization, as shown here. We need to choose the parameters for the safe for the energy function phi, or the barrier function, such that the expected violation of the energy dissipation constraint is being minimized. And here we only take the the positive violation, and if it's satisfied, that gives a negative value, and we just round it to 0. And this is similar to a value activation. Yeah, so if we can find safe this energy function such that this minimization gives us an output as 0, then we say this safety certificate can ensure persistent feasibility. Okay, so this is how we can learn a safety certificate. And then now let's see, if we had a safety certificate, how can we then use that to directly learn an integrated safe control policy? So essentially that is reinforcement learning with state constraint. We want to maximize some cumulative reward, given that the energy is dissipating at every time step. And with this constraint, we can introduce a Lagrangian multiplier to add this constraint to our reward function. And since this constraint is posed on every state along the trajectory, we need to make sure the Lagrangian multiplier is a function that also depends on our state. And so then we get this formulation. This approach is different from the conventional constraint MDP approach, where the conventional constraint MDP is trying to pose a constraint on the kind of overall trajectory. For example, here is posting a constraint on accumulated reward. And since it's not on every state, we can just use a constant Lagrangian multiplier to transform the problem into the following minimax form. But in our problem, we need to like pose the constraint on every state. So then we have a state-dependent Lagrangian multiplier. Okay, then the next step is just to merge these two approaches, the certificate learning and the policy learning. So at the first glance, these two problems may seem like a very different, but if we take a deeper look at the policy learning objective, so this VF-PI is essentially the kind of reward related to the safety certificate. And if we make the safety certificate a variable and then rewrite this Lagrangian term, then we get the following expression, and then we plug in the optimal policy and the optimal Lagrangian multiplier to this expression. We get the following, and we know that if we have an optimal policy already, then this negative value function is a constant. And if we have an optimal multiplier, then this multiplier should filter out the constraint violation. That means if we have a non-trivial or non-empty set of safe control, then this Lagrange multiplier goes to infinity. And if we don't, if we have, then it's going to be 0. And if we don't, it's going to be infinity. That is adding a lot of weights on the safety constraint. And with that, we can rewrite this Lagrangian as a constant multiplying this another constant coming from the Lagrangian multiplier, multiplying this costs associated with the safety certificate, which is exactly the same as the cost we are using in problem 1. And with that understanding, we can actually use a bi-level optimization to solve this joint synthesis problem, where this bi-level optimization has 2 loops. In the inlet loop, we do the policy learning together with the identification of the Lagrangian multipliers. That is going to minimize the worst case energy increase. In an outer loop, we can do the certificate learning, where we try to minimize the worst case energy increase. And in the end, the worst case energy increase will converge to 0. That means we have achieved persistent feasibility. And also the resulting policy is guaranteed to be safe. And we have applied this approach in the safety gym testing environment, although our goal is to apply it in real world autonomous driving tests, but so far we only tested in simulation. And in this environment, the agent here needs to go to the target by avoiding the hazards. We compared our joint synthesis with some hand-designed safety safeguards and also some like a state-of-the-art constraint RL baselines. And we can see that with our approach, we can guarantee that the final safety violation will converge to 0 in all different kinds of situations, as shown in the blue curve. Yeah, whereas another baseline, in some cases, it can converge to 0, but in some other cases, when the safety hazard gets larger, it cannot converge. Okay, so this is how we can like kind of internalize the safeguard and try to learn an integrated safe policy in a relatively complex environment. And the next question is, how can we accurately predict others while the ego vehicle is driving on maybe an intersection? Here we leverage 2 insights. The first insight is that we can have some semantic hierarchy in the prediction, where in a high level, we can predict the insertion area for a vehicle at an intersection. Yeah, because then it can understand the resulting passing order better. And after understanding the passing order, then we can do the low-level prediction. That is what is the actual reference line that the other vehicle is following. And also, given that different vehicles, even they have the same intention, they might still behave very differently. We can introduce online adaptation to our prediction model so that we can better fit the behaviors of specific vehicles. Yeah, so this framework, the general benefit of this framework is that we can use this kind of semantic hierarchy to simplify the state, which will be illustrated in the following slides. And also, since we do this insertion area modeling, so then it can be an abstraction of the real world situations so that it can be adapted and transferable to different intersections or even roundabouts and reuse the same learned results in new situations. Finally, with the online adaptation, we can account for heterogeneity among different drivers. So a more closer understanding about the semantic graph, depending on the insertion area, is shown here. So this is essentially a very compact and general state representation for this driving at intersections or roundabouts, where we take the gap between different vehicles as the state, and the ego vehicle can insert into any gap. And then we will, in order to kind of figure out the relationship between these gaps, we just use a node to encode each gap and then use a bunch of links between those gaps to understand their relationship. And with this modeling, we can then construct a graph neural network and use this attention mechanism to understand their relationships, and then do the training to understand how can we predict the intention of the target vehicle on this semantic graph. Okay, so this is how we do the intention prediction. And after we get the intention prediction, then we care about how we, what is the exact trajectory that target vehicle is going to follow if its intention is to maybe insert it into this blue area. And here we just use a straightforward encoder decoder architecture where we use encoder to get the features, low dimensional features of that vehicle from this first historical trajectory. And then we combine this low dimensional feature with the intention signal from the semantic graph. And then we do a decoder to get the full trajectory prediction. And since the vehicles can exhibit different types of behaviors, even under the same intention, we then add an online adaptation module, which can compensate the error that is measured in real time, and then use that to modify our the parameters in the encoder and decoder in order to better predict the vehicle behavior locally. Okay, then with these two considerations, we then formed this hierarchical adaptable network for driving behavior prediction, where the higher level is using the semantic graph to predict the intention, and the lower level is to use this encoder decoder architecture to predict the trajectory. So let's look at some performance of this architecture. So it actually performs quite good on the intersect data set as shown here. So as we can see, we actually can use this approach to track multiple vehicles. And here we focus our attention on this black vehicle. Oops. Yeah, so and we use this shaded area to predict the insertion in targeted insertion area. So at the beginning, the ego vehicle wants to yield this immediate interacting vehicle, this blue one. And it is predicted correctly. And once the blue one goes away, the ego vehicle or the target vehicle tries to accelerate, and it is going to go before this green vehicle, which is the next immediate interacting vehicle, and that is also correctly predicted. Okay, and so this can also be the same network can also be transferred to a different situation, which is a roundabout without retraining. And this is how the transferred performance looks like. We're still looking at this black vehicle. So at this moment, it's a little bit uncertain whether this black vehicle is going to yield this orange vehicle or go before it. Yeah, but as time proceeds, now it's clear the vehicle is going to yield. And once the orange vehicle goes away, the black vehicle goes forward and try to go in front of this green one. And as the black vehicle travels ahead, at these time steps, there's no immediate interaction. So then the black vehicle just move forward. And now another immediate interaction happens, but this blue vehicle, we predict that it will go in front of the green one without yielding it, and it's predicted correctly. Okay, so this is how we can do complicated prediction in those intersections and the roundabouts. But even we have those prediction to be accurate. If we then consider the prediction in a closed loop system, that is the prediction outcome will affect control, and then multiple vehicles will use the similar prediction and control method to interact with each other, then it's still possible that the vehicles cannot be properly coordinated with each other. And one example we're going to show is here at an unmanaged four-way intersection. Suppose all the four vehicles arrive at the intersection at the same time, and they have the same control strategy, that is to inch forward a little bit to test the response of the others. And if all the vehicles do this simultaneously, then the system can be trapped into this inch stop and inch stop loop. And that is, and this essentially is a deadlock. And the fundamental reason for this deadlock is actually symmetry. Symmetry in the control policies and also the like road geometries. And this is very difficult to solve using by designing a different control strategy. So then our argument is that in this situation, it will be the best to introduce some coordination mechanisms through V2V communication so that the vehicles can figure out who should pass first, but even before they are exactly at the intersection. So here we're showing this kind of V2V communication. If you see links between vehicles, then they're coordinating with each other. And the color of the link means that the vehicle with the same color will yield the other one. And with that, we can see this efficiency at the intersection can be greatly improved. And essentially to enable this kind of communication-based conflict resolution or coordination, there are two types of methods. One is to use graph-based method. One is to use trajectory-based method. So for the graph-based method, the information being communicated is the high-level intention, which corresponds to the insertion area that we had in the prediction part. And for the trajectory-based, the information being communicated is the low-level trajectory. And since information are being communicated differently, we can design different conflict resolution algorithms. So for example, for graph-based, we just need to resolve a conflict graph if the intentions of different vehicles collide with each other. And if we are using trajectory-based communication, then we can use some distributed optimization in a continuous space to make sure those trajectories are not colliding with each other. And here I'm going to use this example to illustrate how a graph-based consensus seeking can be performed. So suppose we have multiple vehicles in the system, and all the systems are designed to behave in the same way. And we just look at how vehicle I is behaving. And all the vehicles will have a communication module to receive information from all the others. And that information is going to be sent to a decision maker. So for example, at an intersection, we can segment the intersection into 4 conflict zones. And each vehicle will know its own trajectory. And so then it will know when the ego vehicle will occupy the conflict zone. Then the time to occupy the conflict zone can be communicated. So for example, vehicle 1 will occupy conflict zone 1 and 2. And vehicle 2 occupy conflict zone 2, 3, 4, vehicle 3, and then vehicle 4. And then if everyone agrees on a first come, first serve conflict resolution mechanism, then we can decide the passing order as shown here, where vehicle 1 will go first, vehicle 3 will go simultaneous with vehicle 1, while vehicle 4 will try to yield vehicle 1, and then vehicle 2 yield vehicle 4. And these updated time slots for passing will then be used as constraints for ego vehicle to do their motion planning. So let's see if there's any constraint posed for vehicle 1. Then the vehicle 1 will just try to compute a trajectory that satisfies that constraint. And usually this constraint is a temporal constraint, that is, you can only occupy the conflict zone in that amount of time. And then if in the next time step, the temporal constraint changes, then the vehicle can update its trajectory to obey that new constraint. And then the actual time that the vehicle will occupy the conflict zone will be broadcasted again to all the vehicles. And we have a we have proved that if this mechanism is designed properly without any packet loss, then it's guaranteed that all the vehicles will converge to a consensus in the end. And yeah, as we see from this figure, the time to occupy the conflict zone will then be broadcasted to everyone, and then the computation can be done again and again while the vehicles are moving forward. Okay, so here is an simulation on using this methodology. And in particular, in this simulation, the conflict resolution is solved directly using this conflict graph, which is a little bit more complicated than the one we shown here. And there are different ways to resolve this conflict graph. And here we list just some solution. But no matter how we build the conflict graph, these are all limited by the resolution of the discrete graph. Yeah, that means if we can just treat the intersection as one conflict zone, then the behaviors will be more conservative than if we treat the intersection as multiple conflict zones. And to mitigate that, we can also introduce the trajectory-based conflict resolution. And in this way, we do not need to limit the number of vehicles in each conflict zone. The vehicles can just figure out how they will move along the intersection by figuring out their corresponding trajectories and optimize their trajectory based on the received trajectory of others. And we can use the distributed optimization algorithm ADMM to achieve that, as shown here. Okay, with that, I would like to conclude my talk. So here, the goal of our research is to achieve this kind of human level driving in very complicated scenario. And here we discussed how can we safely learn the driving policy? How can we accurately predict others in this complicated situation? And then how can we coordinate multiple vehicles? And we hope that we can test this kind of algorithms, integrated algorithms on some realistic environment. With that, I would like to thank you for your attention and acknowledge our sponsors and the students who worked on this project. Thanks.